Well, hello, Sharon Gable here. In this video, I'd like to help you understand plunging folds a little bit better. In my previous tutorials on anticlines and synclines, I was trying to help students understand what those different folds would look like in cross-section views and, more importantly, what they would look like on a geologic map. So let's have a quick look at those non-plunging folds for a second, like the non-plunging anticline we have in this block diagram here. The thing about anticlines is the sedimentary rock layers in the subsurface are warped into an arch-like shape, as illustrated here on this cartoon version of a cross-section down underneath a valley with some elongate mountain ridges on either side, and over here on the right, an anticline exposed in the Canadian Rockies. With a non-plunging anticline like we have illustrated here, the different sedimentary rock layers that are folded into this arch-like structure appear on the surface or on a geologic map as parallel bands on either side of the fold axis. On this side view, which I didn't talk about in my previous tutorials, you can see that the sedimentary rock formations or layers basically look horizontal. And that's because the fold axis in a non-plunging fold like this non-plunging anticline is horizontal. And we can just switch over quickly to look at a syncline for a second. So here's a block diagram of a non-plunging syncline. Again, we have horizontal rock layers in this two-dimensional cross-section vertically down, cut parallel to the fold axis, and we see our characteristic gutter or trough-like down warping of the rock layers in this cross-section cut perpendicular to the fold axis. And again, because this is a non-plunging syncline, our sedimentary rock layers on the limbs of the syncline appear on our geologic map or would appear on the Earth's surface, cropping out in parallel bands on either side of the fold axis in this rock layer that's exposed along the fold axis there. Remember, for a syncline, it's the youngest rock layer that's exposed along the axis of the syncline, whereas for our anticlines, the oldest rock layers of those exposed on the map are exposed along the axis of the anticline. Well, what's the deal with a plunging fold then? In this cartoon, we have a block diagram on top of a non-plunging anticline, right? Because it's got the arch-like shape to our rock layers in the subsurface there. It's non-plunging, I know, because I see the different rock layers on either limb of that anticline cropping out in parallel bands up here on the surface. And because it's a block diagram, I have this second cross-section running parallel to the fold axis, and the rock layers in that view just look horizontal. So the deal with the plunging anticline down here is that the anticline has been tipped into the slide, kind of like upended slide, so that the fold axis is tilting into the slide. So you can see here, the fold axis is no longer horizontal. There's an imaginary horizontal line, and our fold axis here is plunging. In the side view, cut parallel to the fold axis, you can see that the sedimentary rock layers show that plunge. Now, our rule of anticline still applies that the limbs on either side of the axis of the anticline dip away from the fold axis because it is an arch-like shape. And notice that in this cross-section perpendicular to the fold axis, the plunging anticline and the non-plunging anticline look the same. What's different is the map view. We no longer have these parallel bands on our geologic map when our anticline is plunging. Instead, the outcrop patterns for our different rock units wrap around the fold axis and make a V-like shape. So I tried to do this little demonstration in my backyard to show why those outcrop patterns make this V-like pattern on a geologic map when you have plunging folds in the subsurface. So I'm going to grab a piece of poster board paper, and that's going to be a sedimentary rock layer. Originally, sedimentary rocks are deposited in horizontal sheets, but compression will fold them into an anticline, or this arch-like shape. And a plunging anticline is when the anticline is tipped, so the fold axis is no longer horizontal. Now, because I only have 2 hands, I have to set the anticline up on this box. Okay, so there we have a non-plunging anticline with the fold axis horizontal, or at least sort of horizontal, but we're going to tip it, right? So now it's a plunging anticline. What I'm going to do next is grab the camera and try to show you why the outcrop pattern of the plunging anticline makes a V shape. Now remember, erosion is going to wear down through all the different sedimentary rock layers that are folded into the arch-like shape and try to cut it down to a basically horizontal plane. So I'm going to try to draw a line. I'm going to try to keep the line horizontal. I didn't at first, but I'm doing better now. Right? I'm going to try to draw a horizontal line. That would be erosion cutting down through the rock layers to expose them along a horizontal surface in a map view or a horizontal land surface. So now I'm going to turn my plunging anticline into a geologic map, or I don't know, show you the map view of the line. And look, it's a V. It has a V shape. Ta-da! Well, I hope that highly professional demonstration helped. Notice that when we drew the line on the poster board, the V in the outcrop pattern pointed like an arrow in the direction of plunge, like down the steps. And in this diagram, we said that this plunging anticline was tipped into the slide. And see, the V in the outcrop pattern of the different formations points like an arrowhead in the direction of plunge. I just want to show you that, normally when rocks are under compression in the crust, we don't get just one anticline. We get a series of anticlines and synclines, and then if another force pushes all those folds and tips them up on end and makes them all plunge in the same direction, of course, in this case into the slide, our plunging anticlines with those V-shaped outcrop patterns, those V's point like an arrowhead in the direction of plunge. Our plunging syncline in the center here, it also has the V-shaped outcrop patterns to the rock formations that are bent into the syncline. But in the case of a plunging syncline, the V's in the outcrop pattern open toward the direction of plunge. Maybe you can make your own little model with a piece of paper that you fold into a syncline and try to draw a horizontal line on that folded piece of paper and see. It'll make a V-shaped pattern, and that V is going to open in the direction of plunge, or in other words, the direction you have tilted that plunging syncline. Okay, thanks for watching. I hope this helped.